Hey folks, today we're doing isotopes, and we're also going to do a very quick section on mass versus weight because we often get confused with those terms, so I want to go over them. So we're going to start first with just looking at what an isotope is. So to review, when we look at chlorine as an atom, chlorine is Cl. It's number 17 on the periodic table, and the fact that it is a 17 on the periodic table, that tells us that it's going to have 17 protons, and it's going to have 17 electrons. Now this doesn't tell us anything about neutrons. That's where we're going with isotopes, but we're not there yet. Okay, so we need to make sure that we know it has 17 protons and 17 electrons. And to remind us a little bit of an ion, if chlorine takes on a -1 charge, chlorine is still going to have 17 protons. This is always true because of the atomic number of 17. But its electrons this time, it has to have a -1 charge. Remember, electrons are negative, so that means I need an extra electron. So I'm going to end up with 18 electrons in the case that chlorine is an ion with a -1 charge. Now remember Dalton? Dalton had a postulate, and one of his postulates was that all atoms of an element are identical. I told you that that's been disproven, and that's where isotopes come in. So that's why we're talking about isotopes today. Okay, we'll notice with chlorine that there is this thing over here, and this thing is our atomic mass for chlorine. Now remember, if protons have a mass of 1 atomic mass unit, AMU, and neutrons have a mass of 1 atomic mass unit, then how in the world do we get something that's not an integer over here? How do we get 35½? Because you can't have, we already know we have 17 protons, so that's where 17 of it comes from, but can the rest of it be neutrons? Could we have like 18½ neutrons? No, that's not reasonable. You have to have 18 or 19. So there's a problem here, and so that's what isotopes are all about. So what does iso mean? Well, think about an isosceles triangle. What is an isosceles triangle? Well, an isosceles triangle is a triangle with two sides that are the same length, congruent length. Remember this from geometry? Right, isosceles is the same.
Well, that's exactly what isotope means as well. You have two things that are the same. In other words, we have two elements with the same number of protons. So that means they're the same element, right? Sure it does. So if I have two elements that both have 17 protons, they're both going to be chlorine.
Well, let's look at bromine, for example. That's just another one. It's right below chlorine on the periodic table. Bromine is number 35. Since it's number 35, what does that tell you? Sure, it tells you that you have 35 protons. Okay? Well, we've said that isotopes are atoms that have the same number of protons, so they're the same element, but they have a different number of neutrons. So in the case of bromine, in the nucleus, all bromine atoms have 35 protons. That's what dictates that they are bromine, otherwise they'd be something else. However, some atoms of bromine have 44 neutrons, and some have 46 neutrons. Now, the ones that have 44 neutrons weigh about, well, 35 protons plus 44 protons would give you a total of a mass of about 79 atomic mass units. Now, you'll notice that's less than the mass of bromine. Well, we also have some isotopes of bromine that have 35 protons plus 46 neutrons, which gives me a total of 81 atomic mass units, and that's more than this number. So we're somehow in the middle of those. Okay, and we'll talk about how we come up with that number later. Right? Almost all atoms have multiple isotopes. So here we're just looking at 2. In fact, bromine has more than 2, but the majority of bromine are these 2. But there are lots of isotopes of many different elements. So if I look at my periodic table, and I realize this is kind of hard to see, but as I look at these numbers, they're all with lots of decimal points over here. Well, almost all. Technetium's an outlier. For some reason, it doesn't have any. When I get down here to these big guys, all the way down at the bottom, they only have one number there. These guys, too, way down here in the middle, they've only got one number. All right, why is that? Well, let's look at one in particular. Let's look at technetium. Right? As I look at this, I notice it has a 98, and it's in square brackets. And none of the ones around it, all the ones around it have lots of decimal points for their answers. Well, the reason is technetium is made in the lab. And back when I was born, technetium did not exist on Earth at all. And what they have done is they have made it, it's a radioactive element, so it decays. So there was none here when, 100 years ago. But they've been making it for medical reasons, and so now there's some on Earth. But they're making all of it as having one particular isotope. So let's look at technetium for just a second. Technetium, 98, 43, well, it has 43 protons, and all the rest of the mass has to come from the neutrons. So how would I figure out how many neutrons there were? Sure, you just take the 98 and you subtract 43, and 98 minus 43 is going to give you 55. So in this case, there are 55 neutrons in this isotope, the only man-made isotope of technetium. All right, well, here we have hydrogen. The most common isotope of hydrogen has one proton and no neutrons. Well, the one proton is going to give it a mass of 1 atomic mass unit, and there are no neutrons, so your mass is about 1 atomic mass unit. Well, that would kind of make sense, wouldn't it? But there are some other isotopes of hydrogen. For example, there's deuterium, which has 1 proton and 1 neutron, so that would weigh about 2 atomic mass units. And tritium, 1 proton and 2 neutrons, would weigh about 3 atomic mass units. So we do have some other isotopes. They are nowhere near as common as the first one, and as a result, we are much closer to the weight of 1.0 than we are to 2.0 or 3.0. Isotopes with the same element only differ in the number of neutrons. They don't differ in the number of electrons, and they can't differ in the number of protons. So all of these different atoms of hydrogen all essentially have the same chemical properties. The big difference is the mass. So if you had some water that had some deuterium in it, or that had some tritium in it, if you were looking at that water, tasting the water, smelling the water, it wouldn't be any different than the water that you're drinking right now. And frankly, you probably have drunk some water in your lifetime, in fact, reasonably recently, with some deuterium or some tritium in it. All right, let's go back to bromine again. To identify an isotope, we use the mass number. All right, now, what's the mass number? The mass number is the sum of the isotopes, protons and neutrons. So here I will add 35 and 44 together to get 79. Now, that is the mass number. Please realize it is not the atomic mass. This is the atomic mass up here, also known as the average atomic mass. This is not the mass number. Okay, this is atomic mass. And this up here is your atomic number. All right? So you have to remember that this thing here is an average, right? It is not one particular isotope. The particular isotopes are identified by how many protons and how many neutrons they are. You simply add them up to get the mass number. And in this case, we would call this bromine 79. If you remember the last podcast, we were talking about calling things that. Okay. So when I name it, I will sometimes write it this way, with bromine with the mass number up on top and the atomic number down at the bottom. So I would call this bromine 79. The bromine identifies it as having 35 protons, so I don't have to worry about that. So when I call it bromine 79, that's its mass number. Okay. All right. So if I look at these are your mass numbers up here on the left, and it's kind of helpful that we've put the number of protons down here. So you don't even need to look at a periodic table. It doesn't hurt to look at a periodic table. But for example, I can tell that germanium has 32 protons. It always has 32 protons no matter what. Now I have to figure out how many neutrons it has, and the way to do that is 32 plus something gives me 72. Or 72 minus 32 gives me 40. So this is germanium 72. This particular isotope of germanium is going to have 40 neutrons. Now the one down below it is still going to have 32 protons, but this time it's going to have 41 neutrons. And this one down here still has 32 protons, but it only has 39 neutrons, because
71 minus 32 gives me 39. So if I look at germanium, all three of these are germanium. All three of these have the same chemical properties. They bond the same way. They act the same way. They look the same way, etc. Right? The only difference is the number of neutrons when you go in the nucleus. So when you go in the nucleus, some atoms are going to have 40 neutrons, some are going to have 41, and some are only going to have 39. All right, pause the video, see if you can finish the rest of this table, and then come on back and we'll do it together. Okay, so copper has 29 protons because all copper atoms have 29 protons. But 63 minus 29 is 34. So this has 34 neutrons. And 64 minus 29 is 35. So this isotope of copper has 35 neutrons. And how about this guy down here? Now remember, this is Mn, this is manganese, this is not magnesium. Manganese has 25 protons. And 55 minus 25 is 30. Alright, so that's that. Alright, really quick, just kind of digression here to make sure you understand the difference between mass versus weight. Okay, when I stand on a scale in the morning, I weigh about 190 pounds, which we can convert to about 80 kilograms. Okay, but when I go into space, what happens? Yep, when I go into space, I become weightless. I have no weight at all because weight is dependent upon gravity. Right? Well, how about if I were out in space with a spacesuit on? I would still be weightless. Everything I'm wearing is still weightless. If I was on Earth, that would weigh a lot. However, does it take energy for me to move that? Like if I'm trying to turn my back and trying to turn that pack that's on top of my back? Sure, it takes energy. Okay? And that tells me that there's still something there. It may not weigh anything, but it's still there. Right? How about the space shuttle itself? Does the space shuttle weigh something? Well, no, it's also weightless. Once it's up in space, it's weightless. But does it take energy to move it? Sure it does. It takes a lot of energy. And if I were to stand in there and push off with it with my feet, I'm the one who's going to go flying, and the space shuttle is going to pretty much stay there. Why is that? If we're both weightless, what difference does it make? It still has mass. I still have mass. Everything still has mass. Matter still has mass. But it doesn't have any weight. So the mass is proportional to how much matter there is there. Okay? So be very careful. Weight is purely a function of gravity, whereas mass is dependent upon how much matter there is. Okay? So mass is completely independent of gravity. If I weigh 80 kilograms on Earth, I'm still 80 kilograms when I'm in space. But I am weightless. I don't weigh a pound. All right. So in summary, we have a couple of things. You need to be able to determine the number of protons and neutrons for a given isotope, or vice versa. Given the element and the mass number, you should be able to work the other way. Okay. And finally, make sure you know the difference between mass and weight. They are not the same. Okay, that's it, folks. Hopefully you took notes. Please do the isotope worksheet and ask me questions if you have them, and I'll see you in class. Have a good day. Bye-bye.